Hi, this is going to be third lecture on metric spaces. Today's topic is going to be on open sets in metric spaces. Many students have problem with the metric space, not because of they have problem with metric or even perhaps not to do with open balls, but an understanding of open sets. And most often you should like to have some kind of intuitive feeling what it is about. Okay. So as I said in my very first lecture, okay, we will work out a lot of examples. Okay, we have about 5 or 6 examples. Within that, there will be a lot of such possibilities we will look at. So by end of today's lecture, or perhaps I may need one more on this because it's a difficult topic for a beginner. It's actually easy theoretically. Okay, if only the problem arises if you want to have intuitive feeling what it is about. I hopefully by this lecture and perhaps another one, you should be very confident. Okay. Okay. Let us go through that. But before that, I hope you had gone through the last 5 minutes of my second lecture. Do you remember what I proved there? I proved that if I have an open ball BXR, if you give me any Y in the open ball BXR, I can find an S positive so that BYS is contained in BXR. That's what we plan to generalize. Okay, let me share the screen and start doing. We will revisit it. Yeah. So what I have is I have metric space XD, right? And I have a set U, a subset of X. I want to say U is open. Okay. If X has more than one metric, you may want to say is open, D open, or open in the metric D, etc. But if it's clear that we have fixed only one metric, then it's just open. Okay. But what does it happen? So what happens is this is my X. Okay. This is my U. I want to say U is open. That means you give me any X in U, I can find an R so that BXR is completely, the open ball BXR is completely contained in U. Is the definition clear? Are you confident you can write it? Let us do that. Is open if for every X in U, there is an R, this is Rx, okay, positive so that BXR is completely contained in U. You understand that? So if you have an U here, okay, I have this. If I have U here, I have this. If I have U here, I have this. Like that. Okay. So for every X in U, I should be able to find an open ball centered at X, radius R, which is so that BXR is completely contained in U. Then I call it U is open in X or U is open in the metric space. Okay. Have you understood the definition? This is the definition. Okay. Right. Now what we proved yesterday was precisely that. Let X be a metric space and BXR, okay, let us take U to be BXR. Then what we proved that this is open. Okay, this is what we proved yesterday in the last lecture, in lecture 2. Yeah, what did we prove? Give me any Y in BXR. Then we said there is an S positive so that BYS is completely contained in BXR. Right? I hope all of you remember. We also found out what this R should be. This is the picture and this is the thing. And suppose this is the point. Look at this. And okay, this is dxy. And this is the distance we can go. This is up to R. So we did R minus dxy or some such thing. Okay, we found that. So the first thing is an abstract example. What is the abstract example? So this is the first example. Okay. What is example? Any open ball is an open set. X. Okay, just because we have the open ball, it is just for the condition distance between X and Y is less than R. Okay, that is why I call it open ball. But open ball does not mean it's an open set automatically. We have to prove that. How do we prove that? Give me any Y in BXR. I have to find an open ball. Okay, BYX, which is contained in BXR. You follow that? We have proved it. But let's look at some concrete examples now. Okay, pause, review, proceed. If necessary, please open the last 5 minutes of yesterday's lecture 2 and go through the proof of this statement again, once again. If you may remember, I emphasize it's very important. We will keep using it. Now, let's look at the simplest example as usual. So, let us start with R. My D is the standard absolute value metric. Whenever I say standard metric, R, and another. Okay, we have this metric. Okay, right? First, have an intuition. Suppose I have an open ball, interval AB. Is it open? But this is a very trivial question. Why? How many of you remember? We proved that any open interval is actually an open ball, right? And just now we showed that any open ball is open. Therefore, this must be an open set. Do you follow that? So this is utter triviality. But to build intuition, let us try to see. Suppose I take a point. Let's take the point, let us say 0, 1. Okay. And if I take a point here, okay, I want an open ball here. That means I can go up to whatever is the distance. Look at this distance and look at this distance and choose minimum of that. So I can go within that. Okay. Suppose if I have here, okay, let us put a different color. Suppose I have here, I look at this distance and I look at this distance and take the minimum. Therefore, I can go up to this. Are you following me? Yes? Yeah. Therefore, if you give me an X in AB, okay, right? What is the R I can choose? So that BXR is contained in AB. That's the question I'm asking. So now you have an answer, right? Look at this. So what will it be? This R I can choose to be any positive number which is less than, if you want, okay, minimum of this B minus X and X minus A. Do you follow that? This is X minus A. So yeah, X minus A. This is B minus X. And here, this is X minus A. This is B minus X. Choose the minimum. Do all of you agree with that? Okay. Right. Now suppose I have a set of this kind, U, which is A to infinity. This is, remember, this is set of all X in R such that X is greater than A. Is this open? So I have A and everything here. Right? So suppose I start with an X here. What will I do? I can take the interval R to be X minus A. Right? Then add this U. X minus A, then add it 2X minus A. Do you follow that? For any X. Because there is no condition on B minus X kind of thing here. So only thing is how far I can go to this side. Are you following? Please think these are the small examples which will give you how to think of open sets. Okay. Usually, people miss such things. So they make it very difficult. Okay. Let us look at another example. Suppose I have something like A and B closed. This is my set U. Okay. Is this open? Now you should have a picture. See, whenever I have a point here, there is no problem. But if I point X, remember, X equal to B lies in U. Right? Now, what is that I have to do? For every X, I'm supposed to do something. Therefore, if I take an X minus R to X plus R, you can see there are already points here. Okay, these are the dangerous points. Right? This is my X. This may be my X plus R. This may be my X minus R. Therefore, X plus R by 2 will belong to this interval, but that's not going to be new because strictly greater than x. Therefore, this is not open. And how about this? Right? Okay. So I'm sure you know the answer. Let us look some more examples. Right? Okay. Now suppose my u is set of rational numbers. Okay. Is this open? Now how do I imagine? I can't write the picture. But okay, suppose I have r, not r, now let us take x is in q, which is a rational number, right? What do I have to do? If I want to show it's open, what should happen? Okay, if it is if u is going to be open, then there is an r positive, therefore x minus r to x plus r, and this interval is completely contained in the set of rational numbers. Do all of you see a problem here? Yes. Look at these two real numbers, call it a and b. A is less than b. I know what is, okay. You should know your real analysis well, the so-called density of rationals and irrationals. That is given into real numbers a and less than b. There exists an x, okay, or let us not write x now. There is an s, which is a rational number, so that a less than s less than b. And there is an irrational number, so that a less than t less than b. You understand that? This is called density of rationals as well as density of irrationals. This one is called density of rationals. This is called density of irrationals. So this is one thing which all of you should know. Many people have difficulty with metric spaces. One of the main reason is the real analysis they have not learned well. Okay. Teachers are in too much of a hurry to teach continuity, uniform continuity, compactness, connectedness, cluster point, etc. Okay. But the basic things are not taught well. They are kind of brushed away too fast. So you have problem. Okay. And anyway, come back. So what is the conclusion now? We have found out that the set of rationals is not open. Why it's not open? If it is open, there is an r, so that x minus r to x plus r, the open interval, that is bxr, right? That is contained in q. That means it consists of only rational numbers. But on the other hand, the density of irrationals tells me between these two real numbers x minus r less than x plus r, there exists an irrational number t which lies between them. That means the irrational number t lies here somewhere. But then this entire thing is supposed to be contained in q. That's a contradiction. Yeah. So I'm sure you know what is the next question. How many of you know what is the next question? Yes, r minus q, set of irrationals. For the similar reason, the same thing. Now suppose x is not in q, right? Then there is an r positive, so that x minus r to x plus r is contained in set of irrationals. But then there is a rational in between. Okay. So I'm sure all of you are good. So you know how to prove that. Okay. Now let's look at my u equal to z, set of integers. Okay. Is this open? So I have 0, 1, 2, 3, minus 1, minus 2, minus 3, etc. Right? Suppose it's open. What? Then let us take the point 0 in u. Then what do I know? Around 0, okay, I should find an open interval. That means B0R. B0R will be of this form. Right? Okay. This should be completely contained set of integers. Right? Yes. Now, how do you say this is not possible? Okay, it's intuitively clear, right? You will say that, okay, the only integer here is 0, nothing else is there. These are all nice. It's intuition. That's very good. It's important. But if I want a rigorous proof, I should be able to give that. How will I do that? That is why I keep saying, please learn real analysis, real number system well, especially LEV property, Archimedean property, etc. I should learn well. Since R is positive, you know there is a natural number n, okay, so that n times R is greater than 1. That means R is greater than 1 by n. That means 1 by n is less than R. Therefore, 1 by n belong to minus 1 to plus 1. Sorry, minus R to plus R in this interval. Yeah, good. Now you may ask, see, my n might have been 1. In that case, there may not be any problem. No, anywhere. You see that here? Are you following? So if n is greater than or equal to 2, okay, this is not going to be here, right? Because if there is one n, then n plus 1 times r will also be greater than 1. You understand? Therefore, I can as well assume n is greater than or equal to 2, right? That means 1 by 2 should be in minus r to plus r. That's a contradiction. Sorry, that will belong to this, but then that's completely contained in z, therefore 1 by n belong to z. Oh, that's a contradiction. I'm sorry. Whereas this is not equal to, this is equal to 1 by 2 or some such thing. Are you following? Choose an R. So assume there is a natural number n greater than or equal to 2 if you want, so that R is greater than 1 by n. That means 1 by n will be less than R. That means 1 by n belong to this interval. But according to our assumption, that's completely contained in Z. That means 1 by n is an integer. But n is greater than or equal to 2, therefore 1 by n is never an integer. So that's a contradiction. Therefore, this is not open. Okay. So pause, review, proceed. I think this is enough for real numbers. Now let's look at some example. Now let's look at Rn, but again we will stick to R2 for concrete pictorial reasons. Okay. See, yeah, before I go further, there's a very nice result here. Since it will take about 15-20 minutes for me to prove, I don't want to do it, but I may release it as a separate standalone video later. What it says is, if U in R is open, then, okay, U is the union of countably many pairwise disjoint open intervals. Okay, so any open set in R will be something like this. Everything is included. Okay, this will be something like B to minus infinity kind of thing. Even that may be included. Okay, that's how all these things are countably many. Okay, perhaps I will give it as a separate video later, but this is a very important result. Many times people will use it, so learn it. What does it say? You are given an open set U in R, then what do I want to claim? There exists countable family of open intervals. What do I know about that family? The family is pairwise disjoint. What does it mean? Take any two intervals, open intervals in that family. Okay, either they are equal or they are disjoint. Then I want to say use the union of such things. Okay, this result we will see in a different video. At present, let's not worry about it. Okay, now the second example, or this is actually third example, is Rn when n is greater than or equal to, let us assume n equal to 2 for the concreteness sake. And again, remember on R we have various metrics. Okay, there is something very interesting. Okay, I will just state it for the time being. Okay, I will give kind of a geometric proof for that, but we will give a very easy, rigorous proof later. Okay, when you talk about continuity. Okay, what I mean is a subset U in Rn is open in, okay, one of these metrics, if and only if it is open in the other two also. That is, if it is open in one, it has to be open in everything. If it is not open in one metric space, then it's not open in another metric space. The reason is very easy, because remember, we looked at the open balls in, let us call B1, B2, and B infinity open balls. Did you see that? And there was something pattern. What was this? This was B infinity. This must be something like a square. Okay, right? And this was B1 ball. Okay, and we had a B2 ball. You just actually go and touch it. Okay, anyway, you understand? So what we can say is, okay, we, whenever I have a square, right, I can put this kind of open ball which comes from B1. This is correspond to open ball in B infinity. This correspond to open ball here, and I can also put a disk which will correspond to open ball in the D2 metric, right? If it's confusing, just leave it, we will come to it. Let us concentrate on D infinity metric if you want. That will be slightly easier. Okay. Now let's look at an example. Suppose on R2, let me look at this set xy in R2. So that, let us say x is positive. So this one. So my set is this, right? Which is all to the right of the y-axis. Now I want to know this is open. How do I find out whether it's open? Look at the way I looked at the interval, open interval. How did I show? Think of it. Suppose I have a point here. Okay. Then what do I want? I want a D infinity metric, or an open ball in D infinity, or an open ball in D2, or an open ball in D1 should be there. Notice that, for example, I can go up to this, right? This point is xy. Okay. Therefore, how much I can go here? It should not go to this side. Therefore, my R, okay, should be less than mod x. It cannot go this way. And R also should be greater than, less than mod y, because it cannot go this way. Are you following me? Suppose I take something like 1 and 1 by 10. Okay, this is my 1 by 10. Then I want a square around this. So at this point, how much it can go? It can go only up to 1 by 10, right? Whereas here, my x coordinate can go here. Whereas on the other hand, let us look at this. Here I can go only up to this, whereas in the x coordinate I can do this. So what is your guess? So your guess is, if I take B infinity of xy and r, where r is minimum of mod x and mod y. If you want to look at this other one, this case, suppose I have a point here. So I can go up to this, I can go up to this. So what will I do? I will choose the minimum of this. So up to that I can do. I did with respect to D infinity metric because it's a square, but you can also see I can go up to circle, because this is your thing. You understand this? And similarly, suppose this is my x. Okay, I can go up to the circle. So it's also true B2 of same point with R. Okay, this will be contained in U. This will be contained in U. This is not less than or equal to equal to. Are you following? Please pay attention. I just want you to do that. See, in the case of D infinity, you can directly verify. Let us do that. Okay. So let me verify that so that you know the picture told us, but I want to know whether it's true. B infinity of xy r, is it contained in U? That's my question. So start with a UV in BXR. Okay, B. Let me call it only B, right? The ball, this ball B. Then what do I know? The D infinity distance between xy and UV, okay, is less than R. But what is this? This is by definition maximum of mod x minus u and mod y minus v. This is less than r. You follow that? Okay. Now what does this mean? X minus u, mod x minus u is less than r. Remember, x and y are fixed, u and v are variable. Therefore, that means my u should lie in the interval x minus r to x plus r, and v should lie in the interval y minus r to y plus r. For the timing, let us assume xy lies in the first quadrant, just so that, because okay, the same proof works in every other quadrant, but to keep ideas very clear, let me assume this. All right. Now, what is my r? R is less than x. You understand that? Therefore, this is positive. Do you understand this? U belong to this. That means u is greater than x minus r, which is greater than 0, because r is less than x. And similarly, b is greater than y minus r, and remember, r is less than y. Therefore, y minus r is positive. Therefore, u and v belong to the first quadrant. Do you follow that? Yeah? Please pause, review, proceed. Same thing works in any case. Okay? If I keep doing all those cases, then we will never get across. So one or two you should try on your own. All right. Now let's look at the fourth example. Suppose x d is a discrete metric space. Okay. Right. Remember, see, in all the cases you see that to prove something is open, not open, etc. Okay, what we need is something interesting. Look at that. That is why I spent one full lecture on open balls. You see that? I should know how the open balls in a given metric space looks like. That's when I can build my logic or intuition and try to arrive at an R positive so that BXR is contained in U. If I want to prove it's open. Are you following what I'm saying? That is, I'm claiming to deal with open sets, I should have a good idea about how open balls look like in the given metric space. That's the one which allowed me first intuitively guess whether I can put an open ball. Second, I also allowed me to guess what R I should choose properly. Yeah? Okay. Just let's look at this closed U quadrant, first quadrant. This is not open. Okay, this is example 3 continued. Why? Because if you take a point, for example, I can take a point 0. If I take any open ball, okay, around 0, okay, you can see it contains points other than the first quadrant, which are not in the first quadrant. Therefore, this is not open. Anyway, let's come to discrete metric space. Now, do you recall how if R is less than or equal to 1 and positive, of course, do you remember what is BXR? This is only singleton. Right? Now, suppose A is any arbitrary subset of X. Right? And I want to know whether it's open. This is arbitrary. I want to know whether it is open. Yeah? What is that I have to do? You give me an X in A, I have to find an R so that BXR is contained in A. I can take R to be 1 or even half if you want to be extra careful. Then BX of half will be singleton X. That is contained in A. Therefore, what I have proved? I have proved any subset of a discrete metric space is open. Okay, pause, review, proceed. Before we go further, let's look at a technical problem. Suppose xt is any metric space. Let us take A to be empty set. Okay, U to be empty set. Is this open? Now let us look at. Suppose it's not open. What does it mean? If U is open, that means for every X in U, something must be true. Okay. So if it is false, what does it mean? There exists X in U, so that whatever must be true must be false. You understand this? This is a negation, right? Therefore, if U is empty set and if I claim it is not open, that means there exists an X in the empty set for which the result is not true. But empty set has no element. Therefore, logically we conclude U is open. Okay, please repeat the argument. Go through the argument again. Pause, review, and proceed. Okay. And similarly, X itself is open. If I take U to be open, because any BXR, take any X here and any R positive, then BXR is always a subset of U. Therefore, this is always open. These are open sets. Okay, let me see how much time I still have. Okay, 20 minutes. Okay. Now let's look at another example. So, okay, suppose XD is a metric space. Okay, and suppose A is a subset, non-empty subset, okay, of A. Then we have what is called induced metric. Therefore, this is also a metric space, right? Suppose I have V, which is a subset of A, and I say V is open. In where? In the metric space AD. Because the metric space is only AD now. Do you follow that? Please pay attention. This is a slightly subtle point, right? So if you want, I can also draw a picture. So this is my X, okay? This is my A. What I want to know is, I want to know some set open. Okay, this is my B, whether it is open. This is my A. This is my B, right? But as a subset of the metric space AD, whether it's open, right? Okay. Let us assume it's V is open. Okay. Let V be open in this. What does it mean? That means you give me any A in V, which is a subset of A, there is an R positive so that the open ball in A of A R is contained in V. It's a V. You understand this? Do you remember our convention? This is an open ball because the metric D is the same. It's a restriction to A. Therefore, when I write BAR, this is the open ball with center at A, which is a point in A, and R positive. Okay, but it's an open ball in A. I want it to be contained in B. Now you will understand. Do you remember in the last lecture we looked at how do open balls in A look like? Remember how many of you remember? You know that BAR is look at the open ball in X BAR and intersect with A. Okay. All right. So what have we concluded? Therefore, we have concluded, okay, okay, B X A R, there exists R positive, okay. See this for every A, there exists R positive. So I made it wrong. For every A in A, there exists R positive, so that BXR intersection with A is contained in V. If V is open, what have we concluded is this. Are you following? Please pay attention. This kind of switching is what many students are put off. So pay again. If V is open in A, in this metric space A, then give me any point A, there is an R positive, so that the open ball BAAR, that is the open ball, center at A, radius R, which is open ball in the set, in the metric space A, that is contained in B. But we already know this open ball BAR is nothing other than BXAR intersection A. Therefore, if V is open in A, then for every A in A, there is an R positive, so that the open ball BR in X intersect with A, that should be contained in V. Yes? Okay. Why it is very interesting? Okay. I'm going to come to that. Okay. Now let me take a digression. Okay. Suppose U is collection of open sets in any metric space, in a metric space D. Right? So what we already know is empty set X belong to U. And all open balls Bx are also belong to script U for every X in X and for every R ball. These are all the open sets. We had already seen that. Right? Okay. Now suppose I have a collection, sub-collection, okay, call it V. This is a sub-collection of U. You understand that? I am not taking all open sets in X, but only a subfamily of open sets in U. Okay. Then I want to define the union of elements in the subcollection, in the subfamily V. What is this by definition? We will denote it by union. Okay. U, where U is in the subcollection V. This is a notation. This is just a notation. Like when you have U1, U2, UN, you know what is meant by U1 union, U2 union, UN. Or you can write it as UK, K from running to 1 to N. You understand? This is the union. You follow that. But these things are not numbered. They are not indexed. Okay. They're just a collection of subfamilies. I do not know how they are going to be listed. But I want to define the union. What should the union be? It is set of all elements which are in at least one member of the family, right? Therefore, I will write it as the set of all X in capital X, so that there exists a U in the subfamily, so that X belong to U. Please pay attention. This may be the first time you are looking at this definition. Many times teachers simply assume students know and go ahead, but students are very, very what you call uncomfortable with this notion. Okay, so this is something I have collection. There is nothing like U1, U2, U3, U4, etc. You understand? I do not even know how to number. I do not even know whether it's finite. I do not know whether it's infinite, whether it's countable or uncountable. Nothing. But I still want to say union. What does union intuitively mean? Take all elements in any one of the sets. Okay, collection of all elements in each of the sets. That's what we are doing. Look at that. It is a subset of X. How do I define? There is some member of this collection such that X belong to that. That's it. Okay, pay attention. Okay, now I want to claim this. You call it U. I call this U is U naught if you want. U naught is open. So let me repeat. First, let us understand the theorem. I have the collection U of all open sets. This collection contains empty set, the full space X, and any open ball. Okay, whatever the center, whatever the radius. Right? Okay. Now I want to understand some facts about this collection of open sets. So let us start with the sub-collection, subfamily of open sets. Then I want to define the union. I defined it. Okay. That's a union of this. Union of elements in the subfamily B. This is how we define. It consists of all elements X such that X belongs to at least one member of the family script B. Okay, right. Now that is a subset of X. Call that subset U naught. I want to say it's open in X. Now how do I prove that? Yeah. So start with any X in U naught. If X is in U naught, let's go back to the definition. When does X belong to U naught? That means there is at least one U so that U belong to the family V and X belong to U, right? This implies there exists a U in the subfamily V so that X belongs to U. But what do I know about U? Okay, this is a collection of open set. Therefore, this is open. Since X belongs to U and U is open, then what do I know? There is an R positive, so that BXR is contained in U. You understand? Now that's it. We are through. How many of you can see that BXR is contained in U naught? Is it clear? Because start with the Y here, right? Then I want to see whether Y belongs to U naught. But Y belongs to BXR, but BXR is contained in U, therefore Y belongs to U. Since Y belongs to U, U is a member of this collection, okay? Then Y belong to U naught by our definition. Do you follow that? Go slow, okay? Don't be intimidated, because if this is the first time, it will be slightly, okay, difficult for you, but go through it. So what do I want to claim? So I have shown there is an R so that BXR is contained in U, right? All right. Okay. But what I want to prove, I am supposed to prove BXR is contained in U naught. Okay. But it's very intuitively correct. Suppose U1, U2, UN, you call it as U naught, their union. Okay. Then any UI is a subset of U naught, right? Similar things what we are saying. So BXR is contained in U, but I want to claim it is contained in U naught. For that, what I have to do? Start with any Y in BXR. I want to know whether it is in a U naught. But when does Y belong to U naught? That's the reason why I want you to go through, because you will get used to this way of thinking. When does Y belong to U naught? I can say Y belong to U naught only if I can find a U, so that Y belong to U. But do I know that? Yes, Y belong to BXR, but BXR is contained in U, therefore Y belong to U. Therefore Y belong to U naught. Are you happy? Sure? Okay. So we have proved some fact about the collection of open sets. Right? What are the things we have proved? Empty set belong to this, X belong to this. If U is collection of open set, you give any arbitrary sub collection of open sets, that union is also an open set. Yes. So what we have proved is the following: the union of any subfamily of open sets, any family of open sets in X, D is again open. Okay, this is what we have proved. Okay, pause, review, proceed. Now I will tie up this 7 and 6 now. Now let's go back to this. What did I do? B is open in AD, right? That means we saw this happen, right? Okay. Now we know, now suppose U is open in XD. Okay, this is general case. Okay. Now we are in general setup. U is open in XD, right? Now for each X in U, there is an Rx if you want, so that Bx, Rx is contained in U. Now this is a family, Bx, Rx. This is a family. Now it's luckily indexed by this set open U. You understand this? I want to know this like my V, right? What is union of elements in V? That is union. Okay. I will call it only Bx, Rx and X in U. You understand this? This is what we wrote as. Similarly, open set U, U in script V, but any U in here is of the form Bx, Rx. But Bx, Rx depends only on X. Therefore, I am writing X in U. Do you understand this notation? Clear? Spend some time. Yeah. What is any U in script U? It is Bx, Rx. Bx, Rx depends on what? Only on X. Therefore, I am indexing it by X. Yeah. Okay. Right. So, what I have shown now. But notice that Bx, Rx is a subset of U for every X implies union bx or x in u. This is a subset of u, right? But u is a subset of union. Why? Start with any y in u, then y belong to b, y, or y. Okay, but y is in u. Therefore, it belongs to this. You follow that? Therefore, these are equal. Union bx or x equal to union x in u. Okay. Please go through these things because that's why in MTTS we do foundations. This kind of thing is never understood. Teachers rush through because they believe that students know how to talk about union of sets, but then you are dealing with union of arbitrary collection. You follow that? Now let's go back to AD case where A is a subset of X. Then the open set V open in the metric space AD, okay, that is going to be union of B, A, X, or X, where X is in A, X is in B, right? But just now what we saw. But we saw that is same as what is B or X? B or X is BX, X or X, intersection with A, X is in X is in B. Yeah, but this is same as Bx Rx, X is in B, the whole thing intersect with A. Do you understand this? Yeah, you should actually check these things because we define what is meant by union or arbitrary collection. Therefore, it is intersected with A is same as take the union and intersect. Are you following? If ui is a collection, then I have u naught equal to union ui. Then u naught intersection any set A I claim is union ui intersection A. So go to the definition and check it. Okay, this should be an exercise. Please do that. Don't assume, because I know that many students will have difficulty in understanding these concepts. So the best way is go through this and try to prove this. I'm using it here. But what is this? This is an arbitrary collection. X and B is a family of open sets. Where? In X, because this is open ball in X. Therefore, this union is open. Where? In X. Therefore, what do you think you have proved? If V is open in A, there exists an open set V U in X, so that V is U intersection A. This is your U. That's all you have proved. Okay. Have you understood? I know this is extremely difficult part. I very purposely I wanted to do it because this is the kind of thing it's never done. Okay. I'll prove this what I said. If U is a collection, okay, I in I some indexing set and A is a subset, then union of UI intersection with A is same as union of over I in I of UI intersection A. Okay, let us do that. Start with X here. If X belong to that, what does it mean? X belong to union UI and X belong to A. But X belong to union I, this is if and only if. But this is if and only if there is a J in I, says that X belong to UJ and X belong to A. That means there is a J, it's this if and only if X belong to UJ intersection A. You understand this? Now when does an X belong to this? X belong to this means there is a J in I, so that X belong to UJ intersection A. So we have proved it. Okay. Please pause, review, proceed. Okay, as I expected, I will need one more lecture on open sets, but do not be in a hurry. Okay, if you want to master metric spaces and also later you want to go back to general topology as a future course, you should master these things. There the teachers will go through, you will have trouble. Please go through, especially this is from here, it's a steep learning curve from 7 onwards. Okay, please go through it and leave your comments. If you have difficulty in this, I will take it up. So I'll take a couple of more days to release the next video on metric spaces. The next lecture will also be continuation of open sets in metric spaces. So my suggestion is go through, and the best thing will be find another friend of yours, at least one friend with whom you can watch the video, pause whenever there is a PRP, and discuss with him. Okay, you will enjoy. Yeah? I hope you liked it. Take care and stay safe. We'll meet again.